active. Are we active? I think we're active. Welcome to lecture 8 of Submodular Functions, Optimization and Applications to Machine Learning. Today is a particularly important lecture because we will start our discussion of polyhedra and polytopes, and in particular matroid polytopes, after we finish our discussion of some of the geometric properties of matroids. So I hope that you will find today's discussion as interesting as it is, because the theorem that we're going to prove today is fundamental for submodular functions in general, even though what we're going to do first is see it in the context of matroids and matroid rank functions. So we have the same reading, but it hasn't really changed, although everybody is encouraged to read ahead if they haven't read so far. And as a reminder to everybody, we have our first homework. This is not our third homework. Where did that come from, the number 3? Our first homework is due tonight at 11:45 p.m. A number of you have asked questions on the Canvas discussion board, and I think I've answered all of them, I hope, to your satisfaction. But if you have any additional last-minute questions, feel free to contact me. You can come by office hours. Or alternatively, for those of you who wait till the very, very last minute, like literally, I will be online at 11:44 p.m. Okay? So feel free to Skype at that point. Today's lecture 8, so we're going to talk about combinatorial geometries, essentially, which are matroids and why they're called combinatorial geometries. Matroids in the greedy algorithm, which is really important, and then matroid polyhedra. So last time, just as a review, we discussed a number of different operations on matroids, which had sort of corresponding operations that one could do either on the independent sets, or we also saw how it corresponded to an operation done on the rank function to get a new rank function, which thereby defines a new matroid. And that include things like restriction and deletion and contraction, constructing minors, intersection, and union. Okay. We also started to begin to look at various forms of depicting matroids. And what we first thought was, well, graphs are a very, very nice visual, intuitive way of describing most things. We generally like graphs as scientists and engineers because one can visually depict otherwise quite complicated phenomena. And indeed, we saw that in matroids, if it's the case that the number of elements is bounded, namely 3 or more, the number of ground elements, the ground set size, then all matroids are graphic. All matroids can be depicted by a graph. And in fact, here are all of the graphic matroids with ground sizes up to and including size 3. However, it was the case that for matroids with larger numbers of elements, for example, most of the instances that we care about have more than 3 ground elements, is a little bit tricky, and not all matroids are any longer graphic. We defined this notion of an affine matroid, which basically is very similar to a matrix matroid, but we're using the notion of independence based on the affine independence of a set of vectors as opposed to the linear independence, which, as you know, is related based on these properties that are listed here. And we define an affine matroid as essentially the independent structure that arises from a matrix where independence comes from affine independence of column vectors of the matrix. Now, here's where we left off, and I want to sort of, I think there was a little bit of confusion on this example. So what we can then do is we can actually geometrically depict a matroid in some n-dimensional space whereby dependence and independence is described by, in some sense, some notion of affine dependence. And in fact, what we're going to do then is even further generalize that so that it's not necessarily affine independence, but just sort of a geometric structure. A geometric structure that we can sometimes, and in fact quite often, either predict in 2D or projections onto 2D. We can actually describe some fairly complicated matroidal structures. So let's start off with this example again and make sure that this is clear. So this is what we're going to describe as an affine matroid, which consists of 6 elements. So the ground set size is equal to 6. And the dimensionality of the space is 2. And the elements, the matrix, consists of these elements. So these are the column. Each pair is the column vector of the matrix. And the field, we have to designate a field. In this particular case, it's just the reals. So it's a very simple one. And so what we do is then we plot these points in R2 on the right. So this plot here gives the points. Okay, so what we're going to say, just we're designated is that the rank of a set, in some sense, corresponds to one more than, in some sense, the span in the geometry within which this set of points is contained within. Okay, so what that means then is that, so a point normally has a span of dimensionality 1, right? A point is a zero-dimensional thing, so it then gets rank 1. 2 points designate a line, right? So that would be a one-dimensional subspace, or a one-dimensional affine space. But that we do one more than that rank. So then the rank of 2 points becomes 2, and then so basically we have this. So points have rank 1, lines have rank 2, and planes have rank 3. And so we have the notion of flats, like the flat. What are the flats in a matroid? So the flats are these closed sets, right? The flats are the closures, and so a point is a flat, because anytime we add an additional point to a set of point 1, then we can only increase the rank. So a flat is a point or a line or a plane. And all points have equal rank, and all lines have equal rank, and all planes have equal rank. And so what that means right away is that this picture, the rank of this matroid is 3. The rank of the matroid designated here is 3. Okay? So that means that any individual point, like for example, if we were interested in the rank of that point, that would be rank 1. If we take the rank of these 2 points, that would be rank 2. If we take the rank of these 3 points, because they're collinear, that's still rank 2. And this is where the affine nature of the matroid comes about, because the collinearity of the points means that they're affinely dependent, and so therefore they have rank 1 less than the number of points in this particular case, which is 3. But if you were to continue to add points, like if I were to add another point which was also collinear, say there, that wouldn't increase the rank. But as soon as we add another point, say down here, like for example, if we include that set, and now this yellow set is the set of points we're interested in, that's going to have rank 3, like we said last time. But I think it wasn't clear. So 2 points constitute a line. Now, because all 2 non-identical points constitute a line, there's no reason to draw a line between them. So what we're drawing in this picture are only the lines for which maybe it's not immediately obvious. We're only drawing the lines between sets of collinear points greater than 2. Okay? Like we could draw a line here, right? We could draw a line here, and we could draw a line there, and we could draw a line there, and we could draw all these other lines, but they're in some sense extraneous, because we're just saying that all sets of 2 points that are non-identical constitute a set of rank 2. So in general, when we depict this geometrically, we just don't draw that. We don't draw those lines. We just designate them redundant. So in this particular matroid, dependent sets consist of all subsets with greater than equal to 4 elements, right? Why? Because basically the rank of the whole matroid is 3. So if you have 4 or more elements, your rank is 3, so therefore there has to be a dependence somewhere. A dependent set consists of any 3 collinear elements. So this is the example we gave last time. So these 3 elements here are collinear, these 3 elements here are collinear, and these 3 elements here are collinear. And so each one of those sets, the magenta, yellow, and green sets each have rank 2. And then any 2 points have rank 2, and any 3 non-collinear points have rank 3. Right? So 3 non-collinear points constitute a base of this matroid. Why? Because they span the whole plane. That makes sense, right? Now we can actually show other matroids. It doesn't need necessarily to be something that is in R2. We can show an example of a matroid that exists in R3. So here's a projection of an R3 matroid into R2. So just to make sure that the geometry of this is clear. So let's just draw some pictures. So this is a plane. That's one plane. This is another plane. Right? This is another plane. I hope everybody sees it now. And this is another plane. And lastly, this is another plane. So each plane has rank what? It's going to have rank 3, right? So the rank of the total matroid, because it exists in R3, is going to be one more than the projective space within which this matroid exists, and that's rank 4, right? Because we'd span the whole, all of the matroid spans its dimension of space, subspace of space, dimension 3, and the rank is, in the matroid sense, is 1 more than that. Okay. And so basically, all sets of 5 points are dependent because the matroid is rank 4. And then the only other sets of dependent points are the coplanar ones. So, well, the sets of dependent points of size 4 are coplanar. Like, for example, this one, 0, 0, 0, 0, 1, 0. This one is, so it's this one. It's 0, 0, 0, 0, 1, 0, 1, 1, 0, and 1, 1, 0. So this plane, basically, those sets of points, those elements, those 4 elements, are dependent because you only need 3 of them to span the plane within which those points are embedded. Those 4 points are coplanar. And so you can depict interesting geometries just by looking at it matroidally. Now, these are, in some sense, our regular these are embedded in regular Euclidean geometries. All of the things and all of the matroids that are depicted here are correspond precisely to our notion of Euclidean geometry. These are points. We actually have coordinates for each of the points. They're coordinate. This is a difficult word to say. Coordinatizable or something. You can give each point a coordinate in some space, Rn, like a Euclidean space, and the notion of points and lines and planes and hyperplanes and so on and so forth correspond to our sort of usual notion in Euclidean geometry of those objects. And the notion of containment and the notion of parallel and coplanarity and collinearity all exist. But what's interesting about a matroid, and the reason why it's called a combinatorial geometry, is it's not necessarily exactly a projective geometry. It's not like a Euclidean space. And I think the next example. Oh, sorry. Let me just rattle off these facts before we do the next example. I forgot about this. So this is just some facts. So for a matroid, you have a matroid of rank m plus 1 with m less than or equal to 3, say. Then if a subset, so we have some number of points, and so we have a subset x in some geometric representation. So it's like the points, the elements of the ground set of the matroid correspond to points that are coordinizable in this space, Rm. These things are dependent if it's the case that you have 2 or more points and they're identical. So 2 points on top of each other are dependent. And sometimes what you'll do, you'll actually write a point and you'll write like a multiplicity, like 4. These are 4 dependent points. You just write a number next to them. If you have 3 greater than or equal to 3 points and they're collinear, so that means that 2 collinear points are not considered dependent. Those are independent because they have rank 2 and they're equal to the size. But as soon as you have 3 or more collinear points, they're dependent because it only takes any 2 of those points to span that line within which those collinear points are embedded. Okay. Any 4 or more points are coplanar for exactly the analogous reasons. And of course, any 5 or more points are dependent in space. Right? Again, with m less than or equal to 3, because again, the rank in such a matrix is going to be at most 4. Now, loops. This is sort of a little bit of a hack, but in some sense, loops are kind of special case matroidal items. These are individual elements who've got rank 0, so they're immediately dependent. And so what you can do, you can sort of have a special box and just put a loop in them, sort of outside of the geometry. So you don't usually depict the geometry, but you can actually label them. You can just have little boxes and say, because these guys in some sense don't really interact with anything since they're automatically dependent. They have rank 0. They're just sort of useless items. And then parallel items. So remember in a graphic matroid, we said in a graphic matroid, parallel items consisted of, for example, things like this. That corresponds to a multiplicity of points within the geometry. Okay. So that's what I said. So that's identical to saying, so this is the graphic, and this is the geometry. We just say, put a point, and it's 2. So one thing that's really important to realize is that these geometric pictures are very different than graphic matroids. Okay? And so we have this theorem, which is that any matroid of rank up to and including rank 4 can be represented by an affine matroid in Rm minus 1. Okay, so if you're in R3, which we can still visualize, you can represent any matroid of rank up to 4, no matter how many the number of elements. So for very low rank matroids, you can do this. Now, what I was saying before and where I got ahead of myself was that you can go beyond this, because as soon as you get away from the notion of a projective geometry to the notion of a combinatorial geometry, and where this comes from is I have this book, which I own this book. This is Crepo and Rota's book on the foundations of combinatorial theory, combinatorial geometry. So he's the one who had that fantastic quote about the ineffable cacophony of the word matroid and said that they instead should be called combinatorial geometry, because he approached the notion of a matroid from a very different perspective, not from its algebraic sense, like, for example, independent sets and subsets of independent sets and exchange properties. But he approached them from saying that there's some underlying geometry. It's not necessarily Euclidean geometry. It's not necessarily a projective geometry, but it's a combinatorial geometry. And the notion of rank, there's the notion of collinearity and coplanarity, and the notion of rank, if it makes sense, is such that, in such a combinatorial geometry should be such that all maximal independent sets should have the same, rank, right? Or the same size. Otherwise, it wouldn't really make sense to have a rank of a system, because you could have different maximally independent subsets, different size maximally independent subsets, in which case you'd have different ranks. It wouldn't make sense to talk about the rank of the whole system. But a combinatorial geometry does have this notion of a rank. And you can sort of get the idea of why it's called a combinatorial geometry by, let's see if it's worth going over this. So I think I've already kind of said this. So let me just, I don't think we need this. So yeah, this is somewhat redundant. Yeah, I think this is redundant. I just want to move on to this next thing. Okay, so this actually corresponds, so we can actually represent things that are not representable, or that are not coordinizable. Like, for example, here's a geometry, and we can actually, for example, ask if it's a matroid. So here's a geometry which is right now depicted in R2. Now remember, so all 2 points are considered collinear, and so we don't need to bother drawing a line between any sets of collinear points. But any set of 3 or more collinear, considered points that are considered to be collinear, namely they're dependent, any set of such points should have a line between them. So that basically means, like, these 3 points are collinear, so they have rank 2. These 3 points are collinear, they have rank 2. These 3 points are collinear, they have rank 2. These 3 points are collinear. So basically, each one of these lines, which consists of 3 points, are all collinear, they have rank 2. Now there's one set of 3 points which, if this is geometrically accurate, if this was a projective geometry, one would need to have one additional line here. One would need to have this line. Okay? In other words, if it was possible to coordinize this matroid by essentially putting coordinates in some geometric space next to each one of these points, these guys would also have to be collinear. But the question is, what if we don't have that? Do we destroy the matroid property? Do we destroy the matroid property is that it's an independent system such that you have exchangeability, that you can always, if you have a larger independent set, you can always take one from the larger and add it to the smaller. It turns out that this set of points, by looking at all of the independent sets, so remember, all independent sets are sets of size, there's no loops, right? So, and there's no multiplicity, so all sets of size 1 are independent because there are no loops. All sets of size 2 are independent sets, and all non-collinear sets of size 3 are independent. And any one of these sets of size 3 that correspond to a line are not independent. So that basically means that this 3 set of points, those 3 points have rank 3. They're independent. So this is called the non-Pappus matroid. It actually has rank 3. But any matrix matroid that has this set of dependency would require that you have 7, 8, 9 being dependent. So therefore, this is non-matrix matroid. Yep. Sorry?
2, 8, and 5.
I can't hear what you're saying. I'm sorry.
2, 8, and 5 as well.
No, just 7, 8, 9. Just 7, 8, 9. So, sorry?
Aren't they collinear as
Well, that's the thing. We are designating a set of constraints on a geometry. So all we're saying is, okay, find any set of points, find any coordinates that correspond to this set of points. So we have 9 points. This is something that we would need to prove. I'm not saying this is immediately obvious, but my claim is the following. If you were to find any set of coordinates that obeys the current set of collinearity relationships, namely all of these lines, like this one, this one, this one, this one, this one, this one, all these guys. Basically you said, okay, fine, I've got, for any set of coordinates, necessarily it's the case, these guys would have to be collinear as well. Absolutely. That's all the theorem is saying. So therefore, it means that if you were to represent this as in a matroid in some field, these guys would be collinear. These guys would be dependent. However, if you were to just say, okay, let's look at the matroid axioms and designate the set of independent sets by saying everything that's independent is essentially something that's not independent, that's independent according to this picture, you wouldn't be required, you wouldn't be violating the matroid axiom by saying that 7, 8, 9 is independent. Hence, this is a non-coordinizable matroid. This is a non-independent, this is a non-matrix matroid. Which basically means, and any matroid, it turns out that any matroid that has this as a minor is also non-representable. Yep.
So I want to make sure I understand. Could I say, when I see a picture like this, the lines are including the dependencies?
The 3 or more points. And in this particular case, you have so all collinear points, remember, so all 2 points are trivially collinear, but they're independent. The only way that 2 points would be non-collinear, the only way that 2 points would be non-independent, the only way that they would be dependent would be as if they're on top of each other with a multiplicity. That's how we depict that. So that basically means that all single points are independent, all pairs of points are independent in this matroid. And all 3 points are dependent if they correspond to one of these red lines. Right? But since we have not drawn one, this is why I mean it's not a projective geometry, it's a combinatorial geometry, because we're only expressing the dependence relationships in this sort of combinatorial fashion. It is still, in some sense, a geometry. It still has a rank, a notion of a rank. Its rank is 4, right? Whoops. It's still a matroid, but it doesn't correspond to any sort of standard geometry that we know. There are a couple of other examples as well. We can actually use these kinds of figures to ask, is this a matroid? So here's a geometry. Again, this is meant to be embedded in R3. So one plane is this guy, another plane is this guy. Tell me if you're seeing this. That's a plane, this is a plane, and then we have the plane corresponding to this, right? And so the idea is that, like, for example, those 5 points are coplanar, right? So basically, those 5 points that I just outlined in yellow, therefore have rank tricky. 3, yes. Excellent. They have rank 3. How many? These, because it takes 3 points to span that plane, right? Remember, it's a 2-dimensional plane which has rank 3, so it's one more than 2 dimensions within which it works. So points have rank 1, 0-dimensional. Points have rank 1. Lines have rank 2, planes have rank 3. So anything that designates a plane has rank 3. And the only thing that's the points have to be collinear for there to be a dependence of a set of points that have rank 2, and points have to be coplanar for there to be a dependence that corresponds to the points having rank 3. So now the question is this a matroid? Does this correspond to a matroid? Well, how would we do that? Well, one way we know it's a matroid would be we could look at the submodularity of the rank function. So let's look at the rank function. And if the rank function designated by this combinatorial geometry is not submodular, then it's not a matroid. Because remember, what designates a matroid? The rank function has to be normalized, monotone non-decreasing, integer valued, unit increment, and submodular. All of those things. So let's take a look. So let's look at it. So let's designate these two sets, x and y. So x is 1, 2, 3, 6, 7. 1, 2, 3, 6, 7. This is like a flag. It's sort of like a flag shape. So the idea is that that designates a plane. So what's the rank of x? 3, right? So the rank of x is 3. And then say the rank of y. Let's see if this works. Okay, the rank of y. What is y? 1, 2, 5, 6, 7. 1, 2. Oh, sorry. 1, 4, 5, 6, 7. So that's another flag. All right. Do you see how it's a flag shape? You can kind of hold it. Actually, that's a real term that people use in projective geometry. So it's a flag. What's the rank of that flag? Don't be shy. Don't be nervous. Answer the question. Otherwise, I'm going to keep you here late again. So, so what's the rank again? 3. Yes, the rank is 3. So R of x, and what's the rank of x union y? Well, that's a sort of a messy one. So 1, 2, 3, 4, 5, 6, 7. So the rank of everything. So the rank of everything is 4, right? So the rank of everything is 4. So therefore, the rank of the intersection, according to the submodularity inequality, has to be less than or equal to 2. Right? This is just submodularity. Okay, so let's check. What is the rank of the intersection? 1, 6, 7. Well, before I give you the answer, I should say 1, 6, and 7. What's the rank of those 3 points? 3, because they're not collinear. Right? If they were collinear, if they had rank 2, they would necessarily, any 3 points that are collinear has to have a line. That's the rules of the geometry. So therefore, this is rank 3. So therefore, the rank is not submodular. And so therefore, this is not a matroid. This doesn't give you a matroid. Okay. What about this if we add this? If we add this line. Now notice, interestingly, we've added a curved line. So this is where it becomes different from a projective geometry. It's a combinatorial geometry. We are allowed to have sort of continuous lines, curved lines. That's a contradiction. Sort of continuous curves. And continuous curves, if you have a set of points that lie along the continuous curve, that's considered a line. And so basically all points that are on some continuous curve have rank 2. So if we do this, would this suddenly become a matroid? Well, you'd have to verify all the other points. But it turns out that certainly would render 1, 6, 7. It would say that 1, 6, 7 now suddenly has rank. What would that do to the rank of 1, 6, 7? It'd have rank 2, so it would no longer violate that.
Couldn't you say that like 2, 6, 7, 3, all line, one curved line?
2, 6, 7, 3.
They're collinear, one like a curved.
Sorry, which points again?
Like previously we said 2, 6, 7, 3 line planes and they have rank 3.
I mean, you're talking about the flag?
Yeah, the flag.
So the flag 1, 2, 3, 7, 6, this flag?
Yeah, couldn't you, like, because you added that curved line and so this doesn't correspond to necessarily projective geometry. How do you differentiate between that being a plane and that being like a curved line?
Well, as soon as we add this line, we have, it's still a plane because, whoops. Oh, this is kind of a cool example, which I want to show you. But as soon as we add this line, which we did there, this is still a plane, right? It's 2 lines. 2 lines that intersect at a point, which is point number 1.
I'm
Right,
just asking, like, how can you tell apart just like 4 lines that are together in a loop and some curved line?
4 lines that are together in a loop.
Like, basically.
Well, here, what this is, I'm not sure I understand because it sounds like you're asking different things, but I will try to understand both things that you're asking. Which, if they're the same thing, will save time by answering only one of those both things. But here we've got 3 lines, namely that one. Let's use color. Color is our friend here. that one, and this one, right? So these three lines, the red, yellow, sorry, the magenta, I never know what the color they call that. So it's the green, yellow, and magenta, right? So those are three lines that intersect at a point, right? So any two of those lines are considered coplanar, right? Because when you have two lines that, just by the rules of geometry, two lines that intersect at a point define a plane. In fact, two non-skewed lines define a plane, right? Two parallel lines define a plane. But depending on the type of geometry, oftentimes you say that it's always the case that lines intersect somewhere. And so you can sort of designate a point at being infinity. This gets into the notion of sort of when lines are parallel, do they intersect at infinity, and so on and so forth. And usually you just assume that that happens. And so you can designate one of these points. But in this particular case, we have these two intersecting lines. The lines, one line is the yellow line, one line is the green line, and they intersect at that point, and so therefore they define a plane. Another line, but this is not a Euclidean, necessarily Euclidean geometry. It's a combinatorial geometry. So our intuition of Euclidean space no longer applies, but it's still matroidal. And so therefore you call it a combinatorial geometry. It's a geometry in this other space, where you can talk about things like rank. And this is where, I think, when you talk about notions of information, this is getting back to submodularity in machine learning from my own perspective and why we're doing this course and why we're learning about this. Because these combinatorial geometries allow us, when we're measuring sort of information amongst a set of data items of some sort. Like each point could be a data item. And this geometry somehow, and it's non-Euclidean, so it's very flexible. It's not just matrix rank. It's not just having a big giant matrix and saying every point is a column in a matrix. It's much more powerful and flexible because it's not necessarily a Euclidean geometry. It's not necessarily coordinizable in a Euclidean geometry. You can have a lot more interesting types of representations of information and redundancies and things. And this is an example of that. So that's what I'm saying. If you're trying, we can get inspiration from Euclidean geometry, but we can't utilize it forever, because it fails us eventually. Here's another really interesting one. So it's a geometry on 8 points. Now here, in the same way that any 3 points are collinear only if there's a line, here we're saying that any 4 points are coplanar only if, in some sense, there's a plane that designates them. And so here we're giving this set of 8 points, but by just depicting it, this set of 4 points is not coplanar. So let's just draw these set of points really quickly. So what are the points that we're not saying necessarily are coplanar? These 4 points here. So that's not necessarily a plane. Now, is that geometrically realizable? I mean, in some sense, it's like a distorted figure. Like B, D, this thing. Let's use this color. So this plane, could that plane and also this plane simultaneously not be coplanar? But in some sense, what we're saying is that the first one, the yellow one, is not coplanar. And moreover, that plane doesn't even intersect the green plane. There's no intersection. There's no line that intersects it, right? Because that's not depicted. So therefore, it's in some sense a geometry where we have planes and lines and so on and so forth. All these other planes exist. So here are all the other planes. Let's erase them. All the other planes exist, but there's one strange plane, which if this was a cube in a geometry, in a Euclidean geometry, that other plane should intersect the other plane and should be a plane, but it's not. Now the question is, for you to answer, is it a matroid? And if so, is it representable in a geometry? So first of all, you need to check the matroid axiom. This is going to be on your next problem set. You need to check is it a matroid, and so is it representable in some matrix or coordinizable? So there are other interesting geometries. Like you can, for example, express very, very complicated geometries by using the notion of curved lines, even though it's projected into R2. So like, for example, this is considered a line. This is considered a line. I'm just going to draw some of them because I'm going to run out of space. this is considered a line. So let's just, now that we've got some names, so the green set of green points is C, F, I, and J. All of those points have rank 2. The other point, C, the yellow line, curve, whatever you want to call it, C, D, H, and I. Or sorry, C, D, H, and L. I always get this confused. This should be L. Should have drawn it differently, L. C, D, H, and L. That's also a set of points that has rank 2, because it's co-curver. There is no word for that. And it turns out that that corresponds exactly to the dependence relationships that is expressed. It turns out that this thing is representable over G of 3 in 3 dimensions. So G of 3 to 3. So it's the Galois 3 field. So basically, this is just 0, 1, 2 mod 3, and you have vectors of length 3 with coordinates. And that you can actually find a set of coordinates that corresponds precisely to this representation. But here you're depicting it geometrically. So it's a geometry. Here's another one. It's an interesting one that basically, this set of points here, 2, 6, and 4 are dependent. They have rank 2. But so does 3, 7, and 6. Right? So here's a set of points that are dependent. Here's another set of points that are dependent, and so on and so forth. Right? So pretty cool, I think, and pretty powerful stuff. And I think it's a lot of this stuff is not very well known, to be honest, certainly not in the machine learning world. But I think this gives us an easy way to reason about matroidal dependent structures and combinatorial geometries. And you can kind of see why Crapo doesn't like the term matroid. Yeah, question.
So do you spend any time talking to people who do like hypergraph theory? Because these are things that show up in hypergraph. Or these are hypergraphs.
I mean, they're not really graphs because there's a relationship between the set of edges based on, in some sense, the discontinuities between points.
If you have a hypergraph, then you could say like that line, that curved line that had 4 points is just one edge. And then you could reason about it as a graph where each edge has more than 2 vertices. I don't know if it's just like something that looks similar from the pictures, but like in the actual mechanics is different.
Yeah, I might need to think about that. So I know what you're saying in the sense, like, for example, you can say this is one hyperedge here, all right? And all of those curves are hyperedges. And so all of the lines correspond to hyperedges. That's a very good question. Yeah, what I'm thinking about is whether it's possible, for example, to represent parallel lines with this construct. So if you had 2 parallel lines, like that intersect at infinity, like let's say you have that line and this line. Oops, yeah, those 2 lines. I should have drawn a different color. But this line. Those guys are 2 lines that intersect at this other line, which is considered sort of the infinite hyperplane here. If that can be represented by a hyperedge. I think it probably can. So I think that's probably true. I'm guessing that you can. Now it turns out that hypergraphs also, there's the sort of the bipartite neighborhood function, because hypergraphs are like bipartite functions. And bipartite functions are useful for defining submodular functions, as you know. I think that, like, let's see. Let me think about that and get back to you. I think it's a good question. I have a feeling that it's not sufficient. I have a feeling that there's something that we can't do. But I can't come up with an example right now. So this is just a summary. So matroids with ground set size less than or equal to 3 are graphic. Matroids with rank less than or equal to 4 are geometrically represented. These are, in some sense, projective geometries represented in R3. Not all matroids are linear or matrix matroids. And matroids can be seen as projective geometries. In a special case are combinatorial geometries, which is, in some sense, more general because they can do things that projective geometries can't. And I just want to give a little bit of history. So like if you're interested, there's a lot of stuff on this. I think in some sense the people who advanced this theory, this sort of approach, the geometric approach, are really these guys. And they have this book. Like I said, it's right here. It's not very widely read. They have a couple of new versions, but if you look at Crepo and Rota, and then Oxley as well. Oxley sort of, if you want like this, just sort of like a one-stop shop, one place to sort of read up on this, then probably Oxley's the best book right now. The geometry doesn't, Lawler doesn't, while Lawler's an amazing, fantastic book, he doesn't really talk about the geometry of matroids. Okay, of course there's Schreiber as well. Actually, I can't remember. I don't think he talks that much about the geometry. Okay, so let's move on now. So now we have ways of sort of depicting and reasoning about matroids and viewing matroids. We can look at them graphically. We can look at them geometrically. We can look at them even in some sense non-Euclideanly geometrically. But what we want to start doing is moving back to sort of more general submodular functions. And so we want to introduce the notion of the greedy algorithm. And the greedy algorithm, as everybody knows, and as everybody learns in your undergraduate computer science classes, it's often considered a heuristic, where basically you want to sort of optimize something, you want to choose something, and you just basically run this greedy algorithm. And it often works. And I guess you can sort of summarize the greedy algorithm by the following sentence. You can say that the fundamental tenet of the greedy algorithm is to choose next whatever currently looks best without ever having the chance to sort of undo what you've done. So once you've made a decision to choose what you've done, whatever looks good, looks best at the moment, you can't undo it. So in certain ways, it's a little bit like life, because life is it's kind of like you're walking backwards. You always see where you've been, and you never know where you're going. And you just have to, based on what you know, sort of choose best what looks best. And then, but once you've made a decision, like you've made a decision to come to this class, you can't undo having spent the time coming here, right? Hopefully, it will be a good choice for you. Hopefully, life is a submodular function. Now, sometimes actually the greedy can actually give you the optimal solution. Like we've also seen in our undergraduate CS classes that spanning trees, like you can use the max spanning tree. The various forms of greedy algorithm give you the max spanning tree. And also greedy computationally is extremely good because it's fast. Right? You can make it run in n log n time. So it's a scalable algorithm. It's maybe arguably borderline between practical and non-practical, because basically anything that's bigger than n log n is probably not scalable. And even n log n might be too slow in certain cases. But on the other hand, greedy is a heuristic, and it might work poorly in certain cases. And in fact, it's not so hard to show examples where greedy can give you an unboundedly poor solution. For example, supermodular optimization. Greedy is unboundedly bad on the supermodular function. But what we're going to see is that greedy and matroids are just intertwined, inextricably intertwined. They go hand in hand. In fact, that you can use, and I think I've said at the beginning, the very first lecture of the class, that the greedy algorithm working is a defining property of a matroid. And also, I think I said that there are very few constructs, there are very few mathematical constructs that can be defined by the property of an algorithm working. So let's define the greedy algorithm more formally. So let's say that we've got an independent system. So EI, E is our ground set, and I is our independent set. It's not necessarily a matroid. And we've got some modular weight function, W. Okay? Non-negative modular weight function. And here's the greedy algorithm. It's the matroid greedy algorithm. So we start with the empty set. And then we loop. So while there's a set that we haven't chosen, such that if we add it to X, we don't lose independence, we choose the element here that has maximum weight. So in other words, we choose an element that has maximum weight. It's one that we haven't yet chosen. And it's one that if we chose and add to our current set X, we retain independence. Okay, so we choose that, and then we add it to the set. So obviously, at the end of each loop, we haven't violated independence because we never choose. And then basically, we stop at the point when there are no more there's no more items we can add. And for example, like eventually what will happen is this algorithm will run. And what will happen at the end? What will we get? What will X be at the end? Sorry? It's a maximum independent set, which is called a base, right? It's a base. So it's the X at the end will have rank equal to the rank of the matroid. Okay? So another way of looking at this, I mean, this is basically the spanning tree algorithm, right? So it's the same as sorting items by decreasing weight. and then we consider each item, and we add it if it's the case that it's doesn't violate independence. It's a spanning tree algorithm. We add it if it doesn't create a cycle in the graph. Here we're just using the matrix. We need sort of an independence query. Now the theorem we have, which is I think this is an amazing theorem. It basically says the following: is that if we've got an independent system, then the pair is a matroid if and only if for every weight function, for every non-negative weight function, the algorithm leads to an independent set of maximum weight. Okay, so in other words, if it's a matroid, then the algorithm works, and if the algorithm works, then it's a matroid. So therefore, all we need is the algorithm working. So let's just review a little bit. So this is a lecture. This is just remember the matroid by bases definition from lecture 5. It's a review. It's exactly the same slide. So remember, we can say that the bases have this exchange property. That if we have two bases, then we can choose. If we choose one item that's in one but not the other, then we can subtract it from one and add somebody from the other and still have a base. Okay. These are exchange properties. Okay, so what we want to do is prove the theorem. Okay. So any questions about the statement of the theorem? So let's say we've got a matroid, and let's say that this is a solution. This set A1 through AR is the solution returned by greedy, right? And let's say that R is the rank of the matroid, right? So basically, we're going to choose R elements, and we're going to order the elements. This is a construct. This is a thing that we're going to do a lot soon, especially like this is particularly important when we define things like the Lavash extension, the Lavash extension, where we order them in decreasing order by weight. So WA1 through WAR. So A is a base, right? The one returned by greedy, right? And then let's say B is any other base, okay? And we're also going to order these things decreasing by weight. Okay, so they're both ordered decreasing by weight. And so what we're going to show, in fact, is not only that the weight of A is greater than equal to the weight of B, namely that the greedy algorithm gives you the maximum weight in the base, but we're going to show that at every single point in the greedy algorithm, the weight chosen, the item chosen at position I, at every point I in the greedy algorithm, the weight chosen by the greedy is going to be greater than equal to the weight of the corresponding position in any other arbitrary base. Okay. And obviously, if that's true, then this is going to be true, right? So what we're going to do, however, is show this. So to show this, let's assume to the contrary, that there is some position K where the kth item chosen by greedy is strictly less than the kth item in this other base. And remember, we've sorted both of them decreasing by weight, right? And so K is the first position, and so that basically means that for all previous items, for all items less than K, the weight of the item chosen by greedy is going to be greater than or equal to the weight of the item in that other base. Okay? And then we're going to define these two sets. Both of these sets are independent because they're subsets of bases. So A sub K minus 1 is going to be the first K minus 1 items chosen by greedy. And those are all of those items are going to have the property that WA sub I is greater than or equal to WB sub I, because K is the first point. They're all less than K, and K is the first point where this condition isn't true. And let's say that BK is just the first K items of B. Okay. Now, since we have this size, these are two independent sets, and we do know it's a matroid, so we're assuming it's a matroid, and we want to prove that greedy works. That's what we're proving first. So it's a matroid. We have two independent sets that are size, and that basically means that there is some BI that's not an AK K minus 1, so we can find somebody, and the matroid property, we can add it to AK minus 1 and preserve independence, right? That's the matroid property. And because we can do that, we say, well, wait a second, but B was ordered decreasing by weight, right? So that basically means this item that we can take out of B and add it to a chi minus 1, since it was earlier than item k, has weight no less than bk. But by assumption up here, that is less than the kth item of the greedy. But then it's not in a k minus 1, so that basically contradicts what greedy would have done, which is taking the maximum item. So greedy would have said, hey, wait a second, I'm going to choose that item. So greedy would have chosen this item here. And so therefore, this is impossible. So that doesn't happen, and the theorem is proved. Okay, any questions? Okay, so now the converse says, and this is really what's cool. Yeah, question?
Can you explain why WBI is greater than WBK?
Why WBI is greater than WBK? Because we've ordered them decreasing by weight. And remember, I is going to be less than equal, because remember, so because we're choosing BK, right? It's ordered sorry. If you look at this thing here, WBK is the last element, and everything before it is going to be greater than or equal to it. And I is less than or equal to k, so therefore it's greater than or equal to it in B, because we've ordered it. Okay, so the converse basically is an interesting one. This is a theorem. The proof just suddenly pops up. I mean, we're sort of going along, and then it's suddenly there, and you'll be amazed. So given an independent system, it's an independent system. It's not necessarily a matroid. What we do have is that the greedy is guaranteed to give you a maximum independent or set, or maximum weight independent set for any non-negative weight functions, or every non-negative weight function. We don't yet have that it's a matroid. So the independent set is empty set containing a down monotone, since it's already a hereditary system or an independent system. Now, let's say that we take any arbitrary I and j, which are independent, and let's say that I is less than j, and suppose that for all z that are in j, not in I, adding z to I violates independence. Okay, so we're assuming the contrary, that it's not a matroid, but it is the case that greedy guarantees you the maximum weight independent set. Maximum weight. Now, greedy works for any weight function, any non-negative weight function. So let's just define this particular weight function. First of all, let's say that I is of size k. Okay, that's just whatever size I is, let's just say it's of size k. And we're defining this modular weight function to say that, well, if v is in I, then it has weight k plus 2. If v is in the residual of j, not in I, then it has weight k plus 1. And otherwise it has weight 0. So you can sort of define this as, let's say that here's all of the elements. Let's do it this way. Here are all the elements. And let's say that here's I. And here's j. So all of the green elements have weight k plus 2. Right? And all of these, I don't know, blue elements, can you see that? Tell you what, how about let's do it this way. You can see a little bit better. These elements have weight k plus 1. So this is I and this is j here. And then everything else has weight 0. So all of the elements have weight 0. It's a figure that I should have done already. Okay, so basically now what's going to happen? So greedy, after k iterations, basically it's completely free to choose sets in I. And in fact, it's going to immediately after k iterations, it's going to choose exactly I, right? Because those are the maximum weight elements. So it chooses I first, but by assumption, you can't choose anybody in j that's not an I, right? And then anything else it chooses is going to have weight 0. So the weight is going to be, the total value, the maximum weight is going to be k, which is the size of I, times k plus 2, which is the weight of each element in I. Okay, so this is what greedy is going to do, right? Just by the definition of greedy. And now we know, the assumption is that greedy produces the set of maximum weight. But the problem is that J is going to have a weight of what? J is going to have a weight of, it's the size of J times K plus 1, right? It's going to be greater than the size of J times K plus 1, because if that's going to be exactly the weight of J if there's no intersection between J and I. But if there is, then some of the items might have K plus 2, and some of them might have K plus 1. And so that's going to be greater. We know that J is at least of size K plus 1, because we know that I is size K and J is bigger than I, so it has least size at least J plus 1, or K plus 1. And K plus 1 squared is greater than or equal to K times K plus 2. So therefore, the weight of J is bigger, but greedy didn't return it. So therefore, there must be, the assumption that we made must be wrong. There must be a Z such that that's, sorry about this, typo. This should read, there must be a Z such that this is independent. So therefore, it's a matroid. Now, isn't that, I don't know, that's an interesting proof, right? It's basically saying you just find one weight function. You might think, how do you show this for all weight functions? You just find one where it violates, take it to the contrary and prove that it's true. So what does this mean? Let's just summarize. The theorem asks for a modular function, a non-negative modular function. These are just some other facts. I think I have a review over here. I don't think this slide is that important. What this means is the following. Given in independent systems, matroids can be equivalently defined either by all maximally independent sets have the same size. There's a monotone, non-decreasing, submodular, integral, unit increment rank function. Or alternatively, the greedy algorithm achieves a minimum weight independent set for all weight functions. So now there are lots of other ways of defining a matroid, but these are the ones that I'm saying for us are important. Now, can anyone guess why they might be important for us? Because the essential part of any submodular function, namely the polymatroidal part of any submodular function, can be defined by any one of essentially a set of exactly analogous ways as what we've defined a matroid. So what we're going to do is we're going to generalize, and once we start talking about polymatroidality, we're going to generalize the notion of sets. And that's what's going to define submodularity. So keep this in mind, this slide in mind, because each one of these will have a corresponding, each one of these bullet points will have a corresponding definition which will define a polymatroidal function, which we know to be any submodular function plus a modular function. So that therefore means that greedy not only is inherently intertwined with matroids, but the greedy algorithm is inherently intertwined with submodular functions. But submodularity still, as you will see, generalizes matroids. So are there any questions? There must be at least one question. Yep, Scott.
So, does it have to be an integral rank function? Could it just be a polymatroid function?
You mean the generalization?
Yeah.
Well, the matroids are always going to be integral rank functions, and they're going to have unit increment. But as we'll see, polymatroid functions need neither be integral nor unit increment. I mean, entropy we know is a polymatroid function. That's certainly neither unit increment nor integral. It doesn't even need to be rational.
So then polymatroids are defined by polymatroidal rank functions. Is that
Yes.
the statement?
Yeah. We're going to talk about that. I think we're going to. So first, we want to talk about. Before we actually get into that, I want to give you a little bit on matroid polytopes before we get into polymatroidal polytopes. Lots of polys, and we're not even talking about parrots here. Okay, let's take a break. Okay, so we're just going to very, very briefly talk a little bit about convex polyhedra. And I'm going to assume that most people know this stuff. I mean, we're not going to prove any of the deep theorems that are there. But first of all, we would want to define, make a couple of definitions. So a polyhedron in sort of Euclidean space like RE. So everyone should be familiar with what RE means, right? At this point, where basically it's just an n-dimensional space where the dimensions are indexed by elements of the set E, and E is the ground set. And we're saying it's a polyhedron, which is not a polytope. It's possibly open if there exists an m by n matrix A and a vector B such that this set, the set of points, can be described by all x that satisfy that inequality. So it's a polyhedron. And so therefore, we can say that the polyhedron is an intersection of finitely many half spaces, affine half spaces. Affine because B is not necessarily 0. And each half space corresponds to this inequality. Okay? And then a polytope is really defined as the convex hull of finitely many vectors. And so we're in RE, and so we have essentially a bunch of vectors which can be represented as points, and we represent the convex hull of that. It's a convex region, and it's a convex polytope, and that's basically the definition of a polytope. And just by definition, since it's the convex hull of finitely many vectors, and the presumption is that these vectors are finite themselves, the polytope is going, in fact, to be closed. So here's the convex hull operator, which basically takes a set of vectors and then defines all convex combinations of this set of vectors. So convex combinations meaning that basically all coefficients are non-negative and they sum to 1. Okay. Now, we can define a polytope in a number of ways. This is actually a very deep and fundamental theorem in polyhedral theory. So basically, it's saying that it's a subset of RE. So P is a subset. It's a polytope if and only if it can be described by either of the following two equivalent ways. It's either the convex hull of a finite set of points, or if it's a bounded intersection of half spaces. So basically, bounded is sort of the key. So it has to be bounded, meaning that it doesn't have an open face where you can go off to infinity in some direction. Okay? And that these are equivalent is proven. It's a fundamental theorem, which we're not going to prove here, and it's actually not a trivial theorem to prove. But it's this theorem by Fourier, Motzkin, and so on and so forth. Now we're going to see that in some cases it's a little bit easier to prove. Like, for example, when we define polyhedra associated with matroids, it will be possible to show something akin to this theorem for a special case, which is much easier. In fact, we're going to do that presently. The other thing I want to review for you is the notion of strong and weak duality. First of all, like, for example, when you have this particular linear programming problem, you have essentially A is a matrix and B and C are vectors. Then the max of C transpose X time, such that AX is less than or equal to B, the set of constraints, is less than or equal to the min of this. Okay, so this is the dual. This is like the primal, and this is the dual. And that it's an inequality is called weak duality. And since it's linear programming, strong duality exists. And strong duality is basically just changing the inequality to an equality here. And there are a number of conditions for strong duality in both linear optimization and convex optimization, and sometimes even non-convex optimization. In our particular case, we're going to be talking about linear optimization, for which strong duality is guaranteed to hold. Okay? And that's something I think that everyone should be familiar with, especially given that half of you are in the convex optimization class. Now, there's many ways of constructing the dual, right? And we're going to construct a dual. But I just wanted to say one thing about duality. Like, for example, you can say, well, this, when strong duality holds, then this is equal to this. Or you could have a slightly different form of the primal, in which case this is equal to this, and so on and so forth. In fact, all of these basically are just the primals and duals. They're all essentially, all of the primals are in some sense reducible to each other, and all of the duals are correspondingly reducible to each other. And for each primal, there's a fairly mechanical way of constructing the dual. And I can remember myself when I was first learning about this, when I was in junior high school, and I was wondering, how does one intuitively get a good sense of the dual? And from junior high school until I was a tenured professor, No, that's not. That last bit is not true. The first part about the junior high school is true. No, that's not true either. Nothing I say is true. But I remember reading, and this is true. What I'm about to say is true. As a graduate student, no, that's not true because I don't think this book came out when I was a graduate student. However, the following I'm going to say is true. That this book by Vijay Vezarani, I think, has a quote that sort of comforted me greatly when I read it. And I wanted to offer this quote to you as a present, hopefully that you will get as much comfort in as I got when I first read it. And that's basically a notion of the intuition of what a dual is. And so basically what he says is, intuitively, y is one set of equations, and that bell is part of the comfort that you will receive from this quote. So intuitively, y is one set of equations, the dual of another, quite different set of equations, like for example the primal duals that we just saw. So this is a quote from the book, in our experience, this is not the right question to be asked. As stated in section 12.1 of the book, there is a purely mechanical procedure for obtaining the dual of the linear programming. And by the way, let me interject that that mechanical procedure is, I think, beautifully outlined by chapter 5 in the Boyd and Vandenberger book. So if you want that mechanical procedure, look at that book, look at chapter 5, you construct a Lagrangian, so on and so forth. You can get the dual for any of those things quite easily. But once the dual is obtained via this mechanical procedure, one can devise intuitive and often sometimes physical meanings and ways of thinking about the dual. And then using this mechanical procedure, one can obtain the dual of complex linear programming in a straightforward manner. Indeed, the LP duality-based approach derives its wide applicability from this fact. So I was then, when I read this, like I said, comforted by the fact that we don't need necessarily to sort of immediately see or come up with a meaning for what the dual variables are. We go through the mechanical procedure, and then after the fact, we say, oh, this corresponds to costs or something, or this corresponds to prices, or whatever the particular application you have, come up with some intuition for what the dual variables mean. So we're going to take the approach that we know how to construct the dual. Okay, so we've read chapter 5. That's fine, sorry. I'm confused because I have an iPhone too, and I started, so what does Siri say about this? Okay, so one last thing. That's a recognizable tone in this world. So, okay, so this is just review. I don't think we need to do this. So this is just, again, to make sure that this is absolutely clear in everybody's mind what the incidence vector is. So we can talk about a modular function. X of A is equal to the sum for all elements of A of X of A. We can talk about the incidence vector of a set A, which is a modular function which has a 1 for every element in A and a 0 for every element not in A. And so that's equivalent to this. So raise your hand if you have even the slightest confusion about this slide. Because if you do, you're in trouble. Who would raise your hand after that, after such a statement? Nobody. You're not in trouble. I will give you $1 million if you raise your hand. You're still not raising your hand. So, okay. You missed out, you guys. Okay, YouTube listeners, that doesn't count, by the way. So here's one of our definitions of the matroid again. This is one, again, just to sort of do a sanity check. So we have empty set containing down closed, and we can always take an element from the larger independent set and add it to the smaller one, and so on and so forth. Okay, so what we're going to do then is we're going to form a polytope, or a polyhedron actually, associated with the incidence vectors of the independent sets of the matroid. So we've got this matroid, and for every independent set, let's look at its incidence vector, like 1 sub I, and we can actually construct an independence polytope. So this is the convex hull of the incidence vectors of the independent sets of a matroid. And we're going to name this polytope P-ind, or P-ind set. Okay? So that's one polytope. It's guaranteed to be a polytope because it's the convex hull of a bunch of incidence vectors. Now, right away, we have this set. This polytope is itself a set, right? It's a set of real values. The incidence vectors of the matroid are also a set of vectors. And so we have this subset relationship, right? Because the convex hull of a set of vectors certainly contains the original set that's used for the convex hull. And so since that's true, when we look at the maximum weight independent set, the value of the maximum weight independent set, which, by the way, the greedy algorithm solves, that's going to be no greater than this this maximization problem, basically by saying, take the max of W transpose X for all X in this relaxation of the independence vectors of the matroid. Okay? So is that clear? Is this inequality clear? Just a bigger set of vectors. Now let's define another polyhedron, not necessarily a polytope. So this polyhedron is basically defined in this way. And this is the first time we're really talking about this, so I want to make sure everybody really understands this. First of all, here's the name of the polyhedron. We're not necessarily saying it's a polytope. Its elements in Re. It's the positive orthant. And we're saying for all subsets, for all A subset are equal to E, so there's an exponential number of subsets. There's 2 to the size of E possible subsets. We're saying that this inequality must be true. So X of A is less than or equal to R of A. So remember, the right-hand side is the rank of that set according to that matroid, which is this. The left-hand side is basically, this thing is just the sum for A in A of X of A. So this inequality is really, this is less than R of A. So it's a linear inequality, right? So it's a bunch of constraints. It's defining a polyhedron. It's an exponential number of half spaces. Okay? Any confusion now at all about this polyhedron? Any confusion that at why it's an exponential number of half spaces? Now, if we were to take, say, a vector in the P end, what we're going to see right away is that that's going to be in this polyhedron. In other words, the polyhedron is, in some sense, an outer bound of the independence polytope. So in other words, this is true. And we need to prove that. So how do we prove that? Well, this is something that we need to show. So how do we show it? Well, first of all, if it's the case that we choose any x in the independence polytope, then basically it means that there's essentially a set of convex coefficients such that x can be represented as a convex combination of the incidence vectors of the independent sets of the matroid. For some vector, right? Now, it might be the case that that vector has an exponential number, is it exponentially long, right? Because, I mean, how many independent sets are there in a matroid? There could be an exponential many, but that doesn't matter. We're just saying it's representable by assumption. Now, any such x is clearly going to be not in the positive, non-negative orthant. It's not going to have any negative entries, right? Because nothing is negative here. And similarly, or not similarly, also, we have that if we choose any subset A, that if we sum up the elements in A, that's the same as taking this dot product by x times the characteristic vector of the set A, which we can then, when we write x in this fashion up here, we end up getting this stuff down here. Right? So we're just basically putting in the definition of A and multiplying the characteristic vector by every element in every item in this sum, every term in this sum. Now what we do here is then we're just going to say, well, here we've got this bit here, this dot product, right? So that's basically going to be upper bounded by the maximum independent set contained within A. So maximum independent subset of A, right? And so what we can say is, let's consider all independent sets of the matroid. So J is iterating over all possible independent sets of the matroid, and all of those that are subsets of A. And then it's just the characteristic vector of that independent set summed up. So this thing that I just highlighted in green is really just, whenever we evaluate it on E, it's just basically summing up all the elements in this vector. So what this green bit really means is just summing up. This is, what is that? You tell me. That's just basically the size of I of j, right? But it's the size of I of j that's a subset of A, right? It's the maximum size. So this is like finding the base, finding the base of A. And now all of this stuff that we've done here in this green, in this green here, that's independent of that sum. So we can just, and this part here just sums to 1. So basically because of the convex combination. So we've got what left over, we have this stuff. But that's just the rank of A. Okay. So basically means that the rank of A is greater than or equal to the sum for x in A. So therefore, that means that it satisfies all of the criterion for being in this, in some sense, rank polyhedron. And so therefore, this independent set polytope is a subset or equal to the rank polyhedron. Okay, everybody see that? Now, before we move on, let's, what we're going to show is a stronger relationship between these two things. Does anyone want to surmise what that relationship might be? Well, you'll see soon enough. But before we do that, let's take a look at this rank polytope, okay, a little bit more closely. Look what it looks like. So first of all, let's look at it in 2 dimensions. So we've got this rank function. Let's say that there's some matroid. And we've got equations of the following form. So first of all, it has to be in the positive orthant, right? So that means that it has to be, each of the entries are non-negative, both. And then the first entry has to be less than or equal to the rank of V1. The second entry has to be less than or equal to the rank of V2. And the sum of the entries has to be less than or equal to the rank of both items, right? Now, R is submodular, right? And so we have that this is true. Right? That's the submodular inequality. And we have that the rank of the empty set is equal to 0. So we have this is true. And so this last inequality is either causing, is a constraint that's either in some sense touching or it's active, meaning it's actively constraining the set of points that define the set of constraints. Right? And why is that? Because it's basically saying that x1 plus x2 is less than or equal to the rank of v1 plus the rank of v2, in which case it would be touching, if it's the case that the rank of v1 plus v2 is equal to the sum of the ranks, in which case v1 and v2 is independent. Or if it's the case that v1 and v2 are dependent, then the rank is equal to 1, or could even be 0. But let's just say that they're dependent and their rank is 1. And so that would mean that it's active. It's actually actively constraining the set of points. And so here's an example of that case. So first of all, the first inequality is just basically this x1 less than or equal to r1 is all of these points here, right? x2 less than or equal to the rank of v2 is all these points here, right? And then x1 plus x2 less than or equal to the rank of the pair are all these points here. Right? The positive orthant are all these points here, right? We intersect all of them, we get this yellow polytope. So that's our first matroidal polytope. Welcome. Say hello to the matroidal polytope, our first one, because we will be seeing a lot of these kinds of things. There it is again, a little bit closer. But there are other possibilities for this 2-dimensional case. For example, what if it's the case that the rank of the pair is equal to 0? So this is another matroidal polytope. It's just this point. Now don't get confused with these polytopes and the combinatorial geometries that we just saw. And don't get confused with that and the graphic matroids. These are really, really different pictures. This is a polytope here. This is a matroidal polytope. In this particular case, what must v1 and v2 be? We have a name for that. Loops. Right? So if v1 and v2 are both loops, they have rank 0. What if v1 and v2 are independent? Then we have this constraint, which is touching right there. I've got a better picture in a second. But basically it means that the matroidal polytope is this square. And if v2 is a loop, but but V1 is not a loop. So basically, V2 is basically saying that x2 has to be less than or equal to 0, which basically means that the whole polytope is just this blue line at the bottom. So here's another thing. So basically, it's showing possible constraints. So that these two blue guys are the only possibilities. This one or this one. Actually, there's one more, which is this one. But the red ones are impossible. Why are the red ones not possible?
Because they're less than the rank of your individual.
So this one and this one and this one are not possible. Why are the red ones not possible? Sorry.
Less than the rank of an individual. You want to be 2.
Well, you can always have a rank of 0. So why is that? Is it less than? It's not. It's close, but there's, like all of these red guys. Why would that be? So why is that lower left one not possible? Yeah, rank is not negative, right? Why is this one not possible? Because rank is integral. And why is this one not possible? Because the rank is bounded by the size of the set, and we're talking about ground sets of size 2. So we really only have these yellow guys as the possibilities for that constraint. So let's look at it in 3D, because it gets a little bit more interesting. So again, we have non-negative orthants. We have these 3 sort of square inequalities. We've got these 3 pairwise ones and 1 triple. So the kind of thing that it would look like, let's just define a matroid. So let's look at a graphic matroid that's just a 3 cycle. So what does this matroid look like? It's just this. So basically and remember the ground set are the set of edges now. This is not a combinatorial geometry. This is a graphic matroid. Here we're saying that any individual edge has got rank 1, any pair of edges has got rank 2, and any 3 edges, then there's only one set of 3 edges has rank 2. So I just said that. So here's the polytope, the matroidal polytope associated with that. There's 2 angles to look at it. The independent sets are empty set, the singletons, or the pairs, but the triple is not independent. And so what's happening is that the triple, if we look at it in either way, is adding this constraint corresponding to this plane. Or if we want to look at it in another angle, this plane. Okay. But notice a couple of things. These points are at 1. This is 1 here, there's 1 there, and there's 1 there. Right. So it's basically a subset of the hypercube. Right. And we do have that one active thing, which is that one guy. Okay, what do you think the free matroid would be in 3D? What would that look like? A cube, exactly. That's a matroid polytope. Everything's independent. Because there's no longer, we do have one additional constraint, which is this guy, which is touching right at this point, kind of, sort of, and not really reducing any of the set of points. So here's another question. What kind of polytope might this be? I'm not going to answer this, but this is just something to ponder. A couple of things different about it. One is that the one thing that's different about it is that you've got sort of this kind of shape here, meaning it's not just either this or a square. The other thing that's kind of weird about it is that you have this section here. So we will get back to that, but I just wanted to give you a taste of future polytopes. Okay. Any questions on the graphics? Okay. Yeah.
Sorry, could you say kind of in words what that set PR or
Wait, this one? Or
Uh,
which one?
no, just what piece of R plus is. It's like the set of all x that are rank functions.
Not the set of all x that are rank functions. It's basically, this is a polyhedron. This is the rank polyhedron that we defined. And it's basically a subset of Re. So what makes it a subset of Re? Well, first of all, we're taking points in Re. None of the points can be negative. So it's the non-negative orthant. And for all exponential number of subsets of E, this inequality has to be satisfied. So it's an intersection of a bunch of half spaces. Just like any polyhedron, we define a polyhedron as the intersection of a bunch of half spaces. This is a particular polyhedron, which is the intersection of an exponential number of half spaces. And we've come up with examples of them in R2 and R3 that shows that it's not empty. Because obviously, if I took one half space, which was everything to the left, and another half space, which was everything to the right, that would be the empty set, right?
And sorry, could you remember one more time what x of A is? X is a modular function.
X of A is a modular function.
Okay.
And
So modular function of A such that it's bounded by the
Yes.
rank function of A.
yeah, that's right. So we do have that slide. Remember where I said this is important to understand. So
So it's like a class, it's a set of modular functions, non-negative modular functions in a sense.
it's a set of modular functions. You can think of it that way. But remember, any normalized modular function, namely normalized in the sense that x of the empty set is equal to 0, you can think of as a point in Re. Right? Any point in Re is a modular function, right? And it's coordinized by essentially the elements, by the dimensions. Okay. So you can talk about a polytope of modular functions, if you will. Okay, so what we saw a moment ago, or a few moments ago, was that the independence polytope, which was the convex hull of the set of the convex hull of the characteristic vectors of the independent sets of the matroid, was a subset of the rank polyhedron, which consists of this. Right? So we proved that. Now, the relationship that I asked you before to think about was the following. In fact, it turns out that these two polyhedra are identical, and as we will soon see. Okay. Now, the next theorem is really critically important because some people, for example, take this class because they want to understand what the Laplace extension is. This theorem is sort of on the road to understanding what the Laplace extension is. And Laplace extension, as some of you might know, especially from having listened to Lecture 1, is something that's very, very important for structured sparse norms in machine learning, which has become very, very popular. Via the Laplace extension, you can define an interesting sparse norm. But in any event, before we do that, let's actually talk about this particular theorem. So what this says is that we've got some matroid, and we've got a rank function for the matroid, and we've got some non-negative weight function, or a modular function. Then what this theorem says is that there exists a chain of sets, U1 through UN, such that the maximum weight independent set can be expressed as the sum of non-negatively weighted ranks of this chain. Okay? Where moreover, the weight, and the way that we get these non-negative weights, is essentially the weight vector is expressed as the sum of the correspondingly weighted characteristic vectors of the elements of the chain on which the rank function is evaluated. Okay. So let me say this again, just to make sure it's clear. So first of all, this is the maximum weight independent set. We know that this thing is something that's solved exactly by the greedy algorithm when it's a matroid, and we are assuming that it's a matroid. And we're saying the value of that can be expressed. It says that there's some chain of elements, which is basically a sequence of sets, sequence of subsets, which have this containment relationship, such that we can express, first of all, the weight function as the sum of the characteristic vectors of the sets, and then that greedy algorithm result can be expressed as the correspondingly weighted rank values evaluated on those chains of sets. So first of all, how can we then get this weight function? So first of all, any weight weight can be written in this way. So we can write a weight vector W as W1 minus W2 times the characteristic vector of one element plus W2 minus 3 times the characteristic vector of these two elements, and so on, times the characteristic vector of everything but the last element, and then finally the last one times the characteristic vector of the ground set. Okay, so that's just true. Okay, hopefully that's just true. Right. Proof by truism. Right? I think that's pretty trivial, actually. It's trivial. Clearly, that's the word we should be using. Now, if we take W in decreasing order, which we will often do in this class, so let's just sort W in that particular order, then it's the case that all of the coefficients, namely this one and this one and this one, except for the last one, will be non-negative, right? The last one might be negative, okay, but certainly all the others, all the ones that I've highlighted in green, will be non-negative. And in fact, if we were to turn this into R+, if all of the elements were strictly non-negative, then this last guy, Wn, would also be non-negative. Okay? So let's, in fact, do that. Let's take a non-negative weight, or non-negative modular function. Let's sort the elements. So we're going to order the elements, or rename the orders. I mean, in some sense, the axis names don't really matter. Right? We're going to rename the axes such that the axes are named in order of decreasing weight. Okay? It's kind of like sorting the axes. And we're going to define these sets UI as chains defined according to this order. So in other words, U sub I, capital U sub I, is equal to the union, or basically the set of the first I elements according to this order. So what this means is that UI, this UI here, is dependent on the orders, dependent on the W vector, although we don't explicitly write that. Okay. Now, once we've essentially reordered the axes, what we have also is that the characteristic vector of U0, which is the empty set, is just basically the 0 vector. The characteristic vector of U1 is just the vector with 1, and so on and so forth. The characteristic vector of U sub L is a vector that has L1s and n minus L0s in it. Okay. Now we're going to define a set I as those elements where the rank increases according to this order. So it's one set, I, and remember, we're ordering the elements in this particular case, right? Decreasing. And we consider UI plus 1, UI plus 2, and so on and so forth. And every once in a while, what's going to happen is the rank's going to pop up, because we're going to get a new dimension, right? And then any time there's one way you can think of it is like this: the rank increases, then and maybe it increases a lot here, and then it increases. Every one of those increments are going to give us I. So that means, therefore, that equation 8.42, I, is exactly the output of the greedy algorithm. In fact, we even said that that's an equivalent way of running the greedy algorithm, where we sort the vector in decreasing order, and we consider items in that order, and we choose the ones for which the rank increases, or in other words, where we don't lose independence if we were to add it to our current set. And so that therefore means also, moreover, that I is equal to the solution to this maximum weight independent set problem. Because we proved that the greedy algorithm gives you the solution to the maximum weight independent set problem. And it's even a base. Why is it a base? Because the weights are non-negative. Even you could have some 0 guys there too. I mean, it's going to be 0. Once you get to a 0 weight, you just keep choosing any arbitrary ones. You keep doing that until you get a base, in which case you can't anything else. Minimum spanning set. Everything else is going to become dependent. Now let's define going back to this intuition here, what we did a couple of slides ago. Let's see if I can find that slide really quickly. Going back to this, let's define lambda in the following way. So for I is equal to 1 to n minus 1, let's say that lambda is equal to the difference. Again, where everything is sorted in decreasing order, so that means that lambda I is always going to be non-negative. And then lambda n, the very last coefficient, is just going to be equal to the weight of the last element, which is also, because we said that the weight is non-negative, also going to be non-negative. And so we have the weight of the independent set. The weight of this independent set is going to be W of I, which is equal to this thing. This is just summing up, it's just the definition of the weight, which we can write. Now, this is a critical equation. Everybody, please pay attention, okay? This is our first instance of Abel summation. So we can write this as the weight over all weight vectors times the sum of the difference between these ranks, okay? Why is that? Because some of them are going to be 0. Some of the ranks are not going to increase, and so the weight's not going to matter. Whereas some of them are going to increase, in which case we're going to get the weight that actually does matter. Okay? Now we can write this. This is the Abel summation. We can write this in a very different way, where we take out the nth item and put it here. And then the rest correspond to a difference between the weights multiplied times the rank. Because another way of looking at it is like successive terms of this involve the rank function evaluated on the same set. Like, for example, the next, the I plus first term in this guy has the rank at I, and the ith term of that guy has also the rank of I. And so we can combine the two terms together and get this expression here. But that means that we've now written the weight in this particular way, the weight of the maximum independent set in this particular fashion. So it's sum of weighted ranks. Okay, everybody see that? So that basically proves the theorem. So just to make sure that you remember what we're trying to prove, basically we're just trying to show what? We're trying to show that the greedy algorithm, which basically gives you the solution to the maximum weight independent set. Now, I is that maximum weight independent set. This is the value of the greedy algorithm, the output of the greedy algorithm. We can write it in this particular way, where, moreover, we have that the weight vector itself can be written as this characteristic vector, as the sum of the weighted characteristic vectors, which we saw before. Maybe I should just even go back to the proof, the theorem. Okay, any questions? Okay. Let's see if we should talk a little bit more. Yeah, this is, what time is it? Hang on a second. Yeah, I think maybe we should pause or stop here and continue on Monday. So what we're going to do, let me just spill the beans a little bit. What we're going to do is use this fact to prove a fundamental theorem that was originally shown by Jack Edmonds. And in fact, he showed a generalization of this theorem that, namely, the independence polytope is the same as the rank polyhedron. And so therefore, the rank polyhedron is a polytope. But that also, moreover, that theorem is what allowed this sort of fundamental result in combinatorial optimization to be shown, which is namely the polynomial times solvability of submodular function minimization, which is a really deep result. So anyway, are there any questions? Okay. Watch the YouTube video again before Monday's lecture. Okay. I will see you on Monday. Good luck on your homework tonight, and I'll see you later.